So let me get started here. There we go. So first, let's consider the first step that is the part that we already understand from working with VARs, that we have an assembly language program, and then that assembly language program passes to a program that's called the assembler, and the assembler generates the machine language module. And you are used, for example, with the idea that we have pseudo instructions in RARs that are not real instructions in RISC-V. And what RARs does is to convert those instructions into proper assembly language instructions that have a corresponding machine language module, machine language representation. So in this representation here, we assume that all the instructions that are in the assembly language program are instructions that exist in the processor. So oftentimes we are not writing code in assembly, so we write code in a higher level language such as a C program, and then we use a compiler to generate the assembly code. So the path goes from a C program, for example, through the compiler to the assembly language program. And now, after we have that module already assembled, we will go into the executable, that's the actual machine language program. And for that, you need to link the machine representation of multiple modules. And potentially, you may also have library code. So oftentimes you do have library code that you also have to link with the modules that you created. And by linking those together, then you have a full program in machine format, which you then will load that program into the memory of a computer before it can be executed. In this representation that we have here, we are assuming that we're doing static linking. Static linking means that the link between the modules that you wrote and the library code is done one time. And we're going to see when we discuss in a minute dynamic linking, then we're going to understand the difference between static linking and dynamic linking. And what we have here is that there are many compilers that do not use an assembler. Many compilers will generate the object modules directly without requiring an assembler. How we produce an object module? The assembler or the compiler will translate the program into machine instructions and will provide information for building a complete program from the pieces that got assembled. So for example, in C, you may have each file producing one piece, and then you're going to have this complete program that will be built from these building blocks. So this, the file that contains one of those pieces will have a header that will describe the contents of that object module. And there will be a text segment that we are used with the .text segment in our modules when we write assembly program. So the text segment contains the translated instructions. And then there is a static data segment. That's the data that is allocated for the life of the program. So anything that is in the static data segment is present there while the program is running. And then we also need something that's called relocation information. The relocation information is needed for any content that depends on an absolute value of where the program is loaded. So I could, for example, say that a given label in my assembly program is 200 bytes from the beginning of the module. And so this will be relocation information. As I move this module in memory, I'm going to be changing those addresses based on the new base address for the module. So any kind of relocation information needs to be in that file. And then I also have a symbol table. A symbol table contains all the global definitions in my module, plus all the external references. So I will have dependencies expressed in the symbol table. For example, in the lab where you compute the checksum, I could have the checksum standing in a module by itself, and I could have, for example, the main program in a separate module. So the main program will, or the main function will have, that module will say something. I need someone to define a checksum because I'm making reference to a checksum and I don't have it. And the module that has the checksum will be saying, I define a checksum. So that is how those dependencies are resolved. So at the link time, the linker will go through all the modules. In each module will find which functions and which symbols this module defines, and which function and which symbols this module needs. As it goes through all the files, if it resolves all the dependence, then it's okay. If there is a dependence, for example, if I try to compile the main program without having the checksum, so I did not include the checksum in my compilation, then I'm going to get an error saying symbol undefined. And then I also have debugging information, that is how I associate with the source code. So often when you see a bug, when you see an error reported, the line of the source code where that error occurs appear, that has to, this debug information has to be associated with the source code and appears in this object module too. So now that I have several such object modules, I needed to link them together. So how do I link these modules together? What I need is to produce this executable image that then I can actually run in a computer. I'll have to be merging the segments. I'm going to be resolving the labels like I just explained now. And I'm going to not only find out that they are defined, but I also going to find what are the addresses. For example, when I have the function call in main to checksum, it's not enough for me to say where checksum is defined, but I need to know what is the address of the first instruction of checksum. And then I have to have all the path location dependent and the external references that I need to link the module together. I could leave the location dependence to be fixed by a relocating loader. So I could just say, I have this offset from the place where you put this program, and then the loader, when loading the module or when loading the program into memory, will fix all these specific addresses. However, if I have virtual memory, and I know that at this point virtual memory does not make sense for most of you, we're going to be studying virtual memory in detail in November, but if I have a virtual memory, I don't need to do this. The program can be loaded into an absolute location in virtual memory, and then this virtual memory is mapped into the actual physical memory. And again, we're going to study that in detail in November. So now we come to the point where we need to load the program. So I'll be loading from an image file that is in the disk into the memory. So I'm going to be reading the header to find the size of the segments. And then I'll create a virtual address space. Again, the idea of a virtual address space is connected to the idea of virtual memory, which we're going to discuss in November. And I will copy the text and I will initialize the data into the memory. And the other thing that I can do is to not copy anything at all, actually, before I start the execution of the program. There are something called the page tables in memory, and I can simply set the page tables and tell the program to execute a program that's not in the memory, tell the processor to execute a program that's not in the memory. So how that magic works is that when the processor tries to access the first instruction of that program, there will be something called a page fault, and that page fault will then take care of bringing at least part of that program to the memory. I know that this may sound a bit confusing now because we have not studied virtual memory yet. We're going to be studying virtual memory in November, and then this will become more clear. So then I will set the arguments on the stack, and then I will initialize any registers that need to be initialized, such as the initial value for the stack pointer, the frame pointer, the global pointer. So any specific register that has to be initialized for a given processor will be initialized at this point. And then I simply jump to the startup routine, and that starts the execution. We're going to copy the arguments from the command line, for example, and put them into the registers A0, A1, etc. And then I'll jump to the first, to address the first instruction of the main subroutine. And when main returns, I will be invoking an exit syscall to exit the program. So let's look at dynamic linking. Dynamic linking is different than static linking. In dynamic linking, if I have a library that I say I need to link against this library, I'm not going to do the linking actually at compilation time. I'm going to be doing the linking only when I execute the program. So the idea is that I wait until the program is executing to link to the current version of the library that must be loaded in the system when I'm executing that program. So if I'm going to be doing that, I need a procedure code to be relocatable, which means that the code requires the linker to fix a linker to fix the code to run in a new location. So it means that I write a code that does not have absolute addresses. I never say jump to the address 0x8000 because I may move that program somewhere else. So imagine that all your addresses in your code will be relative to a given start position. So position independent coding is assembly code that can run anywhere in memory without changing the assembly at all. So far we are often discussing in questions in 229, we say this instruction is at this address, and the target of this branch is at this address. Whenever I say that in a question, I mean after all this has been done. So at the time of execution, that instruction will be found in those addresses. But when I'm doing the linking and then the loading, my assembly cannot have this fixed static addresses. So there are certain advantages for dynamic linking. First one is that the image, there is no bloat in the image. What does that mean? The image is the file that contains the program that will be executed. Because if I do a static linking, I need to load the entire library with the program and carry that library all the time that I'm executing the program. However, if I do dynamic linking, I may link just a portion of the library, just the portion of the library that's actually invoked during the runtime of the program. You can imagine that I have a program that have many different regions of execution. And some regions of execution of the program will be invoking different functions of the library. So if I do dynamic linking, it's only when a function gets invoked that it needs to be linked. In static link, I need to plan for every possible eventuality, and I need to bring the entire library with me wherever I carry my program. There is another advantage of dynamic linking, is that let's suppose that I have one of the students in the class produce a version for the library today, and that version is fairly good today, but a month from now, another student in the class decides that, oh, I can do the same function much more efficiently because now I understand this code better, or I understand this processor better. So here is a new version of the library, the same library. Now, if a program had been linked against the old version of the library, that old version of the library would stay with that version of the program, or that compilation of the program forever. With dynamic linking, the next time that I execute this program, I can pick up the new version of the library that had been installed in the system, and then I can have all the advantages of this new version. So that's the advantage of dynamic linking. So let's see how I do dynamic linking, how dynamic link actually works. So to do dynamic linking, what you have to do is called lazy linkage. And in computing science, often you're gonna hear the word lazy, and actually you're gonna learn that being lazy actually pays off. Being lazy means to not to do things until you really need to do them. So, and that's what we're gonna do with the linkage here. So let's suppose that you have a call to a library in your program. So what you do, you instead of jumping, doing the JAL straight to the library, you do the JAL to a portion of your program. And what this portion of your program does is to load an address from a table that is our indirection table. So I go and I load that address, and then I do a jump relative to that address. So I put the value that I loaded from the indirection table into a register, and then I do a jump relative to that register. And by doing that, now the first time that I do that, my indirection table will send me to a place where I'm going to be doing the linking. So I have a lot of work to do now. I have to load the routines idea, and I have to do some work to do the linking, because I need to find where in this library is this function, etc. And then I will only then jump to the linker and loader. The linker and loader will do the remapping of dynamic linked library routine into the proper address. So you see that I have quite a bit of work to do the first time that I did this call, and then I get to the dynamic linked code. And then I go back to my program, and what I do now, the second time that I do the call, I go into my indirection table, and now the address that I load from my indirection table has changed, because the process of loading it went and fixed that address in the indirection table. So the second time that I call the very same function from the same library, I no longer need to do all the work of linking that I did the first time, and this is done by having these indirect calls, and that's how I do dynamic linking. So the other topic that we want to talk about in this lecture is the idea of dynamic just-in-time compilers. So they are used in a number of different programming languages. We'll focus here on the Java example. So in Java, you can have a Java program that is then compiled, and after compile the Java code, you generate what's called class files that contain Java bytecodes. And these Java bytecodes are simple portable instruction sets for a Java virtual machine. A Java virtual machine simply executes these bytecodes, and you may also have some library routines that are in machine language that are linked together and are used by a Java virtual machine. And what the Java virtual machine does is to interpret the bytecodes. So this scheme that you have here is what made Java very popular, because Java was a language that was invented to be sent over the internet, and I could create a Java code and send it to any machine, and every machine would have one local Java virtual machine that was able to interpret my Java bytecodes. I did not need to produce a different version of the program for each one of the many processors out there. So the local Java virtual machine would read the Java bytecode, which is universal to all of them, and convert into the assembly code that will run into the local machine. The problem is that the Java virtual machine is interpreting the code, so it's reading the code line by line and translating each line of the bytecode to the assembly code. Well, that's inefficient, because if you go into a loop, you're going to be doing that interpretation of the bytecode many times. Well, that can be fixed by simply buffering the translation, and that was done very early on with Java virtual machines. Still, the performance can suffer quite a bit because you don't have the opportunity to do compiler optimizations that can look at a wider window of your code and optimize. For example, it may figure out that some of the bytecodes are not even needed and they don't need to be executed. If you're interpreting them one by one, might be difficult to find that out. So the field of compiler optimizations is a very mature field. It is my field of research, and there has been more than 40 years of work on, or even longer than that, perhaps now 60 years of work on optimizing programs. And doing an interpretation like is done in Python or is done in Java is not a way to get a very high performing program. So for that, what was invented is the just-in-time compiler. So the idea of the just-in-time compiler is that you're gonna be compiling code into the native assembly of the machine as the code gets executed. And but you could not receive a large piece of Java code and compile the entire code at the highest level of optimization of the compiler when the user is in front of the computer expecting something to happen immediately. So the solution is to start the execution of the Java bytecodes by interpreting them just like the virtual machine always did, and then watch the program executing as it's being interpreted. If some of the functions or some of the methods in that Java program turns out to be executed very often, we'll call those hot methods. And what we're gonna do is to ask the compiler to compile those methods as the program is running. So the way it's done today is that there will be one thread of the machine that will continue executing the Java code through the interpretation. And there is another thread that will be invoked to compile the hot methods. Then, once a hot method is compiled, the next time that the interpreter calls that method, it will not gonna use the interpreted version, it's actually gonna use the compiled version. Well, the machinery is actually more sophisticated than that because we don't have only hot methods and cold methods. What we do, we keep monitoring the execution, so there is a range of temperatures that is used. So we can have warm, hot, super hot, scorching hot methods. The idea is that as a method becomes more and more important for execution, we increase the level of optimization that we do for that method. So my own research group has done extensive work with the IBM Java compiler. And with that work, we end up using machine learning to try to figure out what was the best strategy to compile different methods in a Java program. The short story is that after a couple of years of work trying to improve the compiler that IBM had, our conclusion is that we could not do that. We could not improve the compiler because the engineers had done an excellent job of designing the compiler over the years. But what we showed with our work, that's a work that was published a number of years ago at the Code Generation Optimization Conference. I presented that work in France. And what we found out is that we actually could generate a compiler that was as good as the one that the IBM engineers had worked on for about 15 years to create by training support vector machine, that is a technique used in machine learning, for just a couple of hours. So that was a very positive result, and there was some continuation of that. And we have done significant other parts of work on just-in-time compilation for Java code. So I just want to bring you this part of the story, connecting with the idea of compiler linking load and dynamic compilation, to get you a sense that there is quite a bit of work that still needs to be done to improve the performance of programs, and a significant part of that work is done by compilers and by compilers researchers.